Applications of the derivative.
Section A, critical points.
What can I use the derivative for, you may have asked yourself? Well, the derivative has many applications. The first application of the derivative we will look at is called determining critical points.
Critical points are the points on the graph of a function where the derivative is 0 or the derivative does not exist. These are called critical points because they represent where something important is happening in the graph of the function. You'll see what we mean later. First, let's look at a picture. That's me at the Grand Canyon. Now let's look at a graph.
This is a graph. Looking at a graph allows us to speak geometrically. So, geometrically speaking, at the critical points, the tangent line is either horizontal, vertical, or it does not exist at all at the particular point. On this graph, x equals 1, 3 and 5 are critical points. At x equals 1, the tangent line is horizontal. At x equals 3, the tangent line does not exist. At x equals 5, the tangent line is vertical.
Let f of x equal x cubed minus 3x. Let's find the critical points of this curve.
The first step in finding the critical points is to, you guessed it, find the derivative. Using the power rule for each term, the derivative of x cubed minus 3x is 3x squared minus 3. Do you see how we got that?
The power rule states that if f of x equals x to the n, then the derivative of f of x equals n times x raised to the n minus 1 power. For the current expression we are dealing with, you use the power rule on each term separately to get the derivative of each term. Using the power rule on x cubed gives you 3 times x raised to the 3 minus 1, or 2. So the answer is 3x squared.
On 3x, using the power rule, you get 3 times 1 times x raised to the 1 minus 1. 1 minus 1 gives you 0 for the exponent. Anything raised to the 0 power is 1, so the answer is simply 3.
So, the derivative of x cubed minus 3x is just equal to the combination of the two answers, or 3x squared minus 3.
Next, we want to find the zeros of the derivative.
The zeros are the values of x that cause the derivative to equal 0. How do we find that?
We set the derivative equal to 0 and solve the equation for x. You can see that here. If we factor the expression, it becomes 3 times the quantity, x squared minus 1. We'll divide both sides by 3 to get x squared minus 1 equals 0. Then x squared minus 1 factors into x plus 1 times x minus 1.
We now have an expression times an expression. To solve for 0, we set each expression equal to 0 and solve for x. We get x equals negative 1 and 1. These are the x-coordinates of the critical points.
You see that? We now have the x-coordinates of the critical points of our function.
To find the y-coordinates for our critical points, we simply plug the x-coordinates we just found, negative 1 and 1, back into the original function, f of x equals x cubed minus 3x. Substituting the negative 1 in first, we get 2. So the first critical point is negative 1, 2. Next, substituting in the 1, we get negative 2. So the second critical point is 1, negative 2.
As you can see on the graph, these are your critical points. The slope of the curve is 0 at these points, negative 1, 2, and 1, negative 2, because we found the critical points by finding where the derivative was equal to 0.
And now, another example. Let's find the critical points for f of x equals x to the 2/3 power. Remember, a critical point only exists where the derivative equals 0 or does not exist. So, our first step is to find the derivative of this sucker.
To find the derivative here, we use the power rule to get 2/3 x to the 2/3 minus 1, or the negative 1/3 power. This can be rewritten as 2 over 3x to the 1/3 power. Now, to find the critical points, we have to find when this derivative is equal to 0 or doesn't exist. For the derivative to equal 0, the numerator must be 0, which it never is because it's always 2. So the derivative never equals 0. That's great because we still don't have our critical points.
Our next step is to find where the derivative does not exist. This only happens where the denominator is equal to 0, which is where x equals 0. So there is a critical point at x equals 0.
To find the y-coordinate of this critical point, we substitute 0 for x back in the original function, which is f of x equals x to the 2/3. This gives us 0 to the 2/3 power, or just 0. So the y value is also 0. So 0, 0 is the critical point.
The reason the derivative doesn't exist at 0, 0 is because the tangent line to the curve is vertical there. Remember, the derivative is equal to the slope of the tangent line at that point. Because the tangent line is vertical at 0, 0, the slope of the tangent line does not exist.
An important application of the derivative is finding the critical points of a function. How is this an application of the derivative? Well, we're using the derivative to learn something important about the function. So that's an application. Critical points are the points on the graph of a function where the derivative is 0 or does not exist. You can see this graphically by looking at the tangent lines to the curve at these points. Critical points only exist where the tangent line is either horizontal, vertical, or does not exist.
To find the critical points of a function, there are three main steps. First, you find the derivative of the function. Second, you find the values of x where the derivative of the function equals 0 or does not exist. And third, you substitute the x values into the original function to find the corresponding y values. You put them together and you've got the critical points.
Section B, functions. Are they increasing or decreasing?
Now that we've looked at the critical points of a function, we can turn our attention to the behavior of the function between these critical points. That's why they're critical points, because they tell us some important things about the function. For one thing, the critical points divide the function into intervals where we can determine if the function is increasing or decreasing. A typical function has regions of both behaviors. Here's a graph that shows us what we mean by a function increasing or decreasing. The red dots on the graph indicate the critical points. Basically, a function is increasing when its graph is going upwards from left to right, and decreasing when its graph is going downwards from left to right. Pretty straightforward, eh?
Hey, voice of common sense here again. You know, this increasing, decreasing stuff is all just a matter of good old common sense. If we are looking at the graph like we read a book, from left to right, the function is increasing where the graph is going up and decreasing where the graph is going down. Enough said.
Here's how we tell whether a function is increasing or decreasing over an interval. Believe it or not, we use a derivative to find this out. If the derivative of a function over an interval is positive, then the function is increasing. If the derivative of a function over an interval is negative, then the function is decreasing.
A good way to remember what sign gives what is the pinned principle. Pin stands for positive increasing, negative decreasing. P-I-N-D, pinned. Do not attempt to find the pinned principle in any calculus classroom or textbook. It was developed by a crack team of researchers at Standard Deviant's headquarters, expressly for top secret use of viewers of this videotape.
Now, let's find where this function x cubed minus 3x is increasing and or decreasing.
The first step is to find the critical points, which we did earlier for this function. To do this, we took the derivative of our function and got 3x squared minus 3. Then, setting the derivative equal to 0 and solving for x, we found the critical points to be at x equals -1 and 1.
Now that we have the critical points, in order to find where the function is increasing or decreasing, we need to establish the intervals in which we'll look at the derivative.
The x values of the critical points divide the function into the intervals that we need to look at. So left to right, we now have three intervals. They are -∞ to -1, -1 to 1, and 1 to infinity. We'll see that these intervals represent where the function is behaving consistently throughout, either increasing or decreasing.
To determine if a function is increasing or decreasing, we need to check the sign of the derivative in each interval. Remember that the derivative is equal to the slope of the tangent line. Therefore, if the derivative is positive, it indicates an upward sloping tangent line, and the function is increasing. If the derivative is negative, it indicates a downward sloping tangent line, and the function is decreasing. And if you're really creative, you can draw the pattern for a really scary Halloween costume.
We can determine the sign of the derivative over a given interval by placing any convenient number within that interval into the derivative of the function. In this case, f prime of x equals 3x squared minus 3.
The first interval for this function is -∞ to -1. Let's try inserting a number into the derivative equation from this interval. How about -5? Multiplying out, we get 72, which is positive. If we take any number from the interval -infinity to -1 and substitute it for x in the derivative, we get a positive number.
Because this result is positive, from the pinned principle, positive increasing, negative decreasing, we know that the function is increasing over this interval, -infinity to -1. This can be seen in this partial graph of f of x.
Now let's try inserting a different number in the same interval to prove a point.
Remember, for this interval, the number must fall between -infinity and -1. Let's try -2. Multiply out and you get a derivative value of 9. Since 9 is positive, the function is increasing. This will hold true for any value in this interval.
The reason we can be sure that the function is increasing or decreasing just by substituting in one value is because the critical points identify the only points where the function may change direction. So, the intervals determined by finding the critical points are where the function is the same throughout, either increasing or decreasing.
The second interval is -1 to 1. Let's try inserting a number from this interval into our derivative equation. How about 0? Multiplying out, we get a derivative of -3. Based on this information, we know that if we substitute any number from that interval into the derivative for x, we will get a negative number. And as Pin tells us, a negative derivative means the original function is decreasing over this interval.
We can see this on the graph of the function. Let's add this interval to the one we established earlier. As we can see here, the function is increasing from -infinity to -1 and is decreasing from -1 to 1. Now, let's see what happens in the last interval, from 1 to infinity.
To see what's happening in this interval, we need to insert a number from 1 to infinity. We'll use 2. Multiply it out and you get a derivative of +9. If we substitute any number from that interval into the derivative for x, we will get a positive number. Therefore, like the first interval, the function is increasing for x going from 1 to infinity.
If we look at the graph for the entire function, we can see that it is increasing from -infinity to -1, is decreasing from -1 to 1, and is increasing from 1 to infinity.
Let's slow down for a second and review what we just learned. Okay, we just got some critical points. The critical points divide the graph of the function into intervals where it's either increasing or decreasing. To find out whether the function is increasing or decreasing over a given interval, we simply substitute a value from that interval into the derivative. If the derivative is positive at that value, then the function is increasing over that interval. If the derivative is negative, then the function is decreasing over that interval. To keep from mixing these up, just remember the pinned principle, that little trick we made up for you. PIN stands for positive increasing, negative decreasing. Got it? Whew. Okay, let's move ahead.